All right, good afternoon again. Today we'll discuss about learning rate in machine learning, and we'll talk about various algorithms which are used in both shallow learning and more predominantly in deep learning concepts, which use this learning rate concept, and we'll look at that how what are the problems with learning rate, or why do we need learning rate, and how it can influence machine learning or deep learning algorithms. So we will start talking with basic maxima and minima of function. Then we will look at stationary points. We briefly discussed about stationary points earlier in the course. Next, we will look at the classical optimization problems and how it's relate to machine learning problem. And in that context, we will discuss gradient descent algorithm, which is a optimization algorithm. And we'll look at we will not go into detail of the gradient descent itself in this lecture, because in earlier lecture we already discussed gradient descent in detail. Rather, we will look at the aspect of learning rate in gradient descent, why we need it, what are the problems of it. And in that context, we will first discuss the stochastic gradient descent, and then we'll talk about the concept of momentum or adaptive learning rate, and conclude the session by discussing various adaptive learning rate algorithms. To acknowledge, I mostly took help from these three books for developing this presentation. Most of the algorithms I took from this Ian Goodfellow's deep learning book, and I also used the scanned snippets of the algorithms with marking of page numbers or the algorithm number, so that you can follow it in this book. I also took some help from this book, and ebook you can also download from for this mathematics for machine learning. And finally, this is slightly older book from my undergrad days, but some of the concepts are very well explained in this book, mostly in the about the optimization algorithm concepts. So prerequisite for today's lecture, and I hope most of you already have this prerequisite, is partial differential calculus, the basic concept. We will use partial differential equation multiple times when we talk about gradient descent, and of course the basics of gradient descent and backpropagation algorithm. And if any of you want to revisit, you can I embed this YouTube video within my prerequisite slide, that you can just play this video, and here it will again lead you to the gradient descent lecture here. So I am not playing that now, so let's us move on. So before going into more details about global optima, local optima, etc., let us start from the very basics, maxima and minima of a function. So on the right hand side, you can see a wavy pattern, and it's marked that the gradient or the first derivative is the tangent at any point. And here that gradient is increasing, here it is 0, here it is decreasing, again it is here 0. And at this point, there is a discontinuity in the curve, and here it is not differentiable. So in many of these algorithms, we will assume that these objective functions or the error function, whatever we are talking about, that those are fully differentiable, although we may not be explicitly talk about that. And here is one example when a function is not differentiable. And this is the technical or mathematically correct definition of maxima and minima, which basically means that function is has an extremum point, which means either maximum or minimum, such that in the local neighborhood, the value of the function is either not greater than it or not lower than it. So, and h is a sufficiently small number. So most of us have read about it in our pre-university school days. And in most of our school literature, we mostly discussed up to second degree polynomial and single valued functions or single variable functions, like fy equal to equation of x, where the highest degree of x happens to be up to x square. But here we can also look at higher degree polynomials, and at the same time we can also look at functions with multiple variables. So here are the three theorems that are necessary condition for x0 to be an extreme point of fx is that del fx0 equal to 0. That means the gradient is equal to 0 or parallel to x-axis when it is two-dimensional. In a higher dimensional space, we may not say the x-axis, but del fx0 equal to 0. That is fine. Second theorem says that a sufficient condition for a stationary point x0 to be an extremum is for the Hessian matrix H evaluated at x0 to be positive definite when x0 is a minimum point and negative definite when x0 is a maximum point. So the Hessian matrix, so in our school days, we learned that the second order polynomial, second derivative, that we take the first derivative, equate it to 0, then we take the second derivative. If it is less than 0, we tell it is maximum, greater than 0 minimum. But the problem is that the second derivative, we usually tell that it is indicates us the curvature of a curve. But then whenever we tell curvature, we try to visualize it either in a curve in 2D or in a plane or curved plane, which is in 3D. But when we are talking about, say, many variables, then if it is more than 3 variables, then of course we cannot visualize it. So this Hessian matrix, which we'll see in the next slide, that it's a way of measuring the curvature of a higher dimensional space. And if at a stationary point y0 of fy, if the first n-1 derivatives vanish and f and y is not equal to 0, then at y equal to y0, fy has an inflection point if n is odd and an extreme point if n is even. And this extreme point will be maximum if the nth derivative at y0 is less than 0 and minimum if the nth derivative at y0 is greater than 0. So if you put n equal to 2, then you will get exactly what we have been taught in our school days differential calculus. Okay, so we'll see an example of that. So when we are talking about Hessian matrix, so a Hessian matrix is it's a square matrix of second order polynomial. So this is the generic formula, and this is the expansion of the generic formula. And it describes the local curvature of a function in many variables or curvature of a higher dimensional space. Just like the second derivative gives us an idea about the area of curvature of a 2D case or a 3D case. And this is Ludwig van Hayes, and slightly out of the topic. So Hayes was born in Koisenberg, and if any of you remember your graph theory, you may remember this famous 7-bridge problem of Koisenberg, which is the same town which was later solved by Leonhard Euler. So he was born in this old Prussia, present Germany, and the Hessian matrix is named after him. So this is one particular example of this is a 4th order polynomial and this is a 3rd order polynomial, and here although the third theorem may look complicated, but if you just follow it or keep on derivating the function up to its highest degree, it will be pretty easy to see. And here you can see that the 4th order polynomial has a minima at y equal to 0, while the 3rd order polynomial, it has a stationary point, but this is neither a maxima nor a minima, rather it is an inflection point. So with this background, we may now look at that what are the why these are relevant for our machine learning problem. So in classical optimization algorithms, what we try to do, that exactly what we are discussing so far, that we try to find maxima or minima of an objective function, and often we also have a set of constraints. So based on the constraints, it becomes a constraint satisfaction problem. Sometimes the constraint can also be in terms of the possible solution. For example, the solution can also only be integers, then it becomes a integer linear programming problem. And then based on the objective function, we have various type of optimization problem, convex optimization, non-convex optimization, linear, non-linear, etc. In machine learning algorithms also, as we already saw for fitting straight line or the backpropagation derivation, that we try to minimize the loss function between the actual and prediction. And in that way, that machine learning algorithm in both cases, both in classical optimization and machine learning, we try to find the extremum point of a function. In case of optimization problems, we tell it objective function. In case of ML algorithms, so we call it the error function. Now we can readily convert a machine learning problem into an optimization problem. How? So say that we have a true distribution of data x and y. Here we are telling x and y because y is, we will use various notation, and I will explain this equation in a second. So x is your input variable, y is the output variable. Now here you can readily see one difference with classical optimization algorithm, that in classical optimization algorithm we have an objective function. In case of a machine learning problem, I have a data set. So this data set, say we have a training data set where I know the classes or the values in a regression problem. So from this existing data set, we try to estimate, or we try to guess the actual distribution of data. So here EXY, that it is the same expectation, and the EXY for this empirical distribution. And here first I will tell the notations because that will help us to understand. So this P cap data XY is the empirical probability distribution of training data, because this is what we have. We do not know the true distribution. If we knew that, then it becomes a classical optimization problem. Next, we will use this L. L is the loss function. And then we use this fx theta, where theta is the model parameters. So when we are fitting a straight line, the model parameters are only the slope and intercept. When we are training a neural network, the model parameters are the weights of individual connections. And this loss function, it is y is the predicted value. So the loss function is calculating the difference between the actual versus prediction. And we, in most cases, it is the RMS error, we can assume. And we are adding that for m is the number of training examples. So we are adding it for all the training example. And we are calculating this expected value. And this way we can, and we of course this expectation maximization. So the same EM concept, that we want to try to maximize this expectation, or by maximizing, or what we generally do, that we can maximize the negative of the error, which actually means that we are minimizing the error. So that way we can convert a machine learning problem into a classical optimization problem. But then there are some differences between classical optimization and machine learning problem. And based on that, we will have our rest of the lecture where we will see that what we can do about it. So in optimization problem, we know the objective function. And then we have a set of constraints or other conditions. But in ML, we try to estimate it from training data set. In optimization problem, we try to find the optimum. That's why it's called optimization. We are trying to find maxima, minima. In machine learning, many times it's good enough that if we can only reduce the value of the error function up to a limit which is acceptable for practical purpose. Next, the stopping condition. Optimization algorithm stops only when the gradient becomes very small, which may be a local optima. While the machine learning algorithms have specific stopping condition, one such or most important stopping condition may be that when the overfitting begins to occur, that means the machine learning model is memorizing or the true distribution rather than generalizing. And this is one particular example where we plotted the training and test validation error with respect to the number of epochs or number of times we are training. And this can be the stopping condition, that after where, although the training error is reducing, so from the optimization point of view, you will say that let us move on and on, because as long as it becomes training error becomes asymptotic to the x-axis. But in machine learning, we are also observing the error in the validation set. And since after this point, the validation error is increasing, so we understand that now the model is, although the training error is reducing, but the model is started to overfit. So we should stop it here. We should not go any beyond. And finally, optimization algorithm works on an objective function, as we told, but many times the machine learning algorithm offers on a surrogate loss function. And example of surrogate log function is log likelihood, in which case we take a logarithm of the actual error function. And the advantage is it's difficult to calculate product, but by taking log, we convert a product function into a additive function, and which is easier to deal with. And the machine learning algorithm will work on the surrogate loss function instead of the actual loss function. And many times it will give a better generalization that more or less same thing that we just discussed. A better generalization means that it will generalize well for unknown data set, which beyond the training data set. So here, just a quick revisit of the gradient descent algorithm, that we follow the gradient or the first derivative and try to find that when it is equating to 0. And this is the formula for the straight line fitting example, where we have this error into x is the input data and the learning rate. So in the derivation of the del J del M or del J del B, where J is the error, we did not have this parameter. The answer comes only x into error, but then we introduce this learning rate. And this is how we actually change the model parameter. M is the slope, B is the intercept, and the del M is calculated from here. And this is the formula for straight line fitting. And this is just a snapshot of the backward pass of the backpropagation algorithm. Here also you can see that we have the same RMS squared error, and we are differentiating it with respect to the weight here, and then we are breaking it up based on the functional dependency, that the weight depends on the first output and the output depends on the net coming from the previous layer, and that depends on the W5 weight here. And basically here we have only two model parameters that it's easy to memorize or understand. Here we have many model parameters, but basically the calculation is exactly same, that we partially differentiating the error with respect to individual model parameters. And the error calculation is also like this quadratic function of the RMS error. So when we do gradient descent, that how we are putting the training data together. So in earlier lecture, we discussed about the load balancing problem, that we have to balance the number of samples per class or the throughout the distribution of the data set equally for getting a best performance. But then when we have a small set of training data, we divide it into a cross validation set 90%, 10%, and give the whole training data set for training. So that is called the batch learning. But when our training data set is very large, then it can create a problem that each epoch or each training cycle will take too much time. But in reality, what we want, the gradient descent algorithm can perfectly work if we can empirically estimate the direction of gradient change, that whether I should increase a model parameter or whether I should decrease a model parameter. So in the stochastic gradient descent, what we do, that we sample a mini batch of M example from the whole training data set, and we estimate the gradient with respect to this small subset of the full data set. And it can be proven that by taking this random sample from the full training data set, we make an empirical estimate of the expected value of gradient. And as long as we can, this estimate is unbiased, and that we can ensure by proper load distribution among various class, that the gradient, we are getting the correct direction of the gradient, we can converge the algorithm even without batch processing. And many times these size of the mini batch can also relate with the GPU architecture. And if it matches the GPU architecture, the batch size, then we really have performance upgrade. That means the algorithm can converge much quicker than a full batch processing. Here we again use the concept of the learning rate here, and here we are again can visualize the effect of learning rate for gradient descent. The learning rate decides that how fast we are changing the gradient. So these are some typical cases of learning rate. So when it is good, then it is gradually the loss function gradually decrease, and then it becomes asymptotic to the x-axis with more number of epochs. If it is very high, then it may happen that we can miss the optima or the convergence. So you can think about that I have a bowl with many ups and downs inside, or maybe, yeah, you can assume that I have a bowl, but I have some ups and downs inside, or maybe some people play with a game where we have concentric circles, and I have to bring a ball at the middle of those concentric circles. So if I shake it very much, then the balls will just keep on bouncing, but they will not change their existing place. While if I move it very slowly, then the ball will take too long to go to its designated place. So a low learning rate slow down the convergence. A very high learning rate may fail to converge, while a high learning rate can converge to a wrong value, or may not reduce the error functions adequately, while a good learning rate will reduce the error function gradually, and then finally it will converge to the minimum value. So a small learning rate, summarizing, slows down convergence, while a large learning rate may overshoot minima and can even fail to converge, as we saw in the yellow line in the previous figure. So next question is that how to find the best learning rate. So can we adapt learning rate across iterations or across epochs? That as I am training the network, I am getting the network is understanding the data even better. So can we adapt the learning rate accordingly? And secondly, can we have different learning rates for different model parameters? So in the case of a neural network, we have many weights. If it's a deep neural network, then we have more layers and more connections. So do we need to use the same learning rate for the whole network, or can we use different learning rates for different model parameters? So here is one case that here you can see that this is showing, you can imagine that the training, you can imagine it's like that a ball, just as I was giving this particular example of the game that many of us played in the childhood, that we have a flat pan and we have some concentric circles towards that, and we try to bring some small metal balls inside the middle of the concentric circles. So as if this small ball, it is going back and fro and trying to reach the center of the circle. So let us look at the first possibility, that if we can adapt learning rate across iterations. So here comes the concept of momentum. In physics, as we know, the momentum means that mass into velocity. In this case, we consider a unit mass and we try to measure velocity. Velocity means the rate of change. So a very basic algorithm may be that if I see that the gradient is changing in the same direction, I can increase the amplitude of change. Similarly, if we say it is decreasing in the same direction, we can increase the amplitude. But if it is opposite, that is going up and down, then we can reduce the rate of change. And some physical analogy can be that you can think about a pendulum, and as if I am damping the pendulum so that it reduces the to and fro oscillation, or I am adding more weight or making it heavier so that it stops going back and fro, rather it try to follow in the same direction. So here is one example in terms of mathematical notation. So this is the loss function, if you remember. xi is the input at ith iteration, theta are model parameter, y are the predicted values, and I am adding this error for all training samples, and del is the derivative. Just think about in the gradient descent algorithm that we have the e, and then we are differentiating the e with respect to each and individual model parameters. It's exactly same that we are differentiating with respect to theta, the model parameters. And then we are calculating this velocity, and this alpha and epsilon, these are small values, and we can choose them based on empirical measurement, or also there are some estimation techniques of epsilon. But generally we hard code them to a small value, and we will see that how the effect of alpha helps us in the convergence process. And instead of the gradient del m, we use the velocity to change the model parameters. So these are the two examples. So in this case, we use the momentum, means that we increase the change when the direction of change, the direction is not changing. That means the gradient is changing in the same direction. And here you can see that along this axis, here really there are big oscillations. While this is an example where we didn't use momentum, and there here in the picture you can see that you can assume that this is a small canal or a small thin valley, and this ball or the agent, it's rebounding so many times on the walls before going towards the center. But in this case, what happens that it is rebounding less number of times, because when it is going this way, we are increasing it. When it is again changing direction, we are also increasing the amplitude. So it is rebounding less number of time, or it's converging in less amount of time on iteration. So when we use the momentum. Next, we can have the same stochastic gradient descent algorithm with momentum, and the only change here is that earlier we are changing that with respect to this gradient. So if I just go back to a few slides here, you can. Okay, I think I will. Sorry, I will just go back to that slides on the stochastic gradient descent here. So here you can see that G is compute gradient descent gradient estimate. This is, and then we are directly applying the update to the model parameters by multiplying the gradient estimate with epsilon. Okay, theta minus epsilon G. But next, let us move forward to this stochastic gradient descent with momentum. And here you can see that we are computing this velocity update from the gradient estimate, and then we are changing the model parameters based on this velocity instead of directly from the gradient itself. So when we will update this velocity, there is another modification is instead of moment update. So in this case, we are first estimating the gradient. We are estimating the gradient, and then we are updating the velocity. In this case, while in case of instead of moment update, what it tells that we first update the model parameters, and then we calculate the gradient descent, gradient estimate. So here you can see the gradient step and moment step. This is the actual step. But here we look ahead gradient step, and then we take the actual step. So this we first update model parameters, and then we calculate the gradient descent. In some cases, this instead of moment update have some advantage over the stochastic gradient. So in this way, we can adapt the learning rate across iterations by looking at the change of direction of the gradients, and by increasing them when they are changing in the same direction. Next, we can look at that can we have different learning rates different model parameters that we in a neural network, we have many model parameters, all the weights. So can we change these weights based on different learning rate? Now we cannot hand code it because in a deep neural network or even in a shallow neural network, see individually. So can we have an algorithm by which we can find a formula to update them differently? We need not to do them all in the same way. So this class of algorithms known as adaptive learning rate algorithm, and the basic algorithm is very similar as we just discussed, called delta bar delta algorithm. It's an early heuristic approach to adapt individual learning rates of model parameters. So if the partial derivative of the loss with respect to a given model parameter remains the same sign, then the learning rate should increase. And if the partial derivative changes sign, then the learning rate should decrease. And of course, this kind of rule can only be applied to full batch optimization when we are, instead of stochastic gradient descent, we are using the full batch for optimizing. And this is very similar that we just described, that when the gradient is changing same direction, we will increase the amplitude. When it is changing its changing direction, that means we will decide that we should slow down the change. So we'll reduce this parameter and we'll do it for each individual parameter. Slight sophisticated algorithm is the AdaGrad algorithm. This also individually adapts the learning rate for all model parameters by scaling them inversely proportional to the square root of the sum of all the historical squared values of the gradient. So here on the right hand side, you can see that I have plotted a very basic function that this parameter I am changing based on the historical parameters. Okay, and this graph is not coming from any machine learning example. I just created it for explanation. So here this yellow line, this is the actual error or the E. And when I am updating E based on this old choice, so in AdaGrad what we are doing that we calculate this square root of sum of all the historical squared values, and the parameters with the largest partial derivative of the loss have a correspondingly rapid decrease in the learning rate, while parameters with small partial derivatives have a relatively small decrease in the learning rate. The net effect is greater progress in the more gently sloped direction of the parameters case. So basically what we do that we calculate the error and then we keep on accumulating the error. So in this case, I put the value of alpha equal to 1. And here you can see that how the value of this parameter changing when we am accumulating the older values. And then I put the other two curves by changing the value of alpha to 0.5, which you can see is kind of following the original error curve. And this is alpha equal to 0.9, which is also initially increasing, but then decreased. So in AdaGrad, one problem is that it can be proved for convex function. It converges and it gives good results for convex functions, but not too well for non-convex function. And one reason is that this AdaGrad algorithm keep on accumulating the error. So it's scaling them inversely proportional to the square root of the sum of all the historical squared values of the gradient. So the sum of all the, it's take the sum of all the historical squared values. Okay. So in the next algorithm, exactly that problem has been taken care of, that instead of taking the cumulative sum in the root mean square propagation algorithm, we take an exponential moving average. So here we used, you can see that what happens to the graph when I use different values of alpha. And it has been shown that in the non-convex function, the root mean square propagation algorithm works better than the AdaGrad algorithm. And here on the right side, you can see such a graph from a paper where they compared various adaptive learning rate algorithms. This is the number of iterations and this is the training cost. And in a more modern algorithm, the Adam optimizer, it tries to inherit the strength of or the positive attributes of the both AdaGrad and RMSProp algorithm. and it uses both first and second moments of gradient to adapt learning rate for individual weight of neural network. So I did not put the details of the equation of the RMSProp and Adam optimizer here. And please note that both RMSProp or Adam optimizer, it can be used with stochastic gradient descent with either the naive momentum that we discussed or with the Nesterov momentum. And you can follow these hyperlinks and of course the book by on deep learning by Ian Godfellow for a more detailed description of the algorithms. And initially when the Adam algorithm was published, then initial results show that it was working pretty well. But later on, it found that it has some problems for classification, some image classification task. So one particular paper, for example, for the image classifications task, they used Adam optimizer at the initial iterations of the learning, and then they switched to the stochastic gradient descent after the algorithm crosses boundary conditions, and that way they got a better convergence. And still now people are still undertaking research on adaptive learning rate based algorithm, and which can lead us to the final slide that of course after all this algorithm, your question will be which algorithm should we choose, and the frustrating result is there is currently no consensus on this point. So we discussed about, we started the talking about momentum, stochastic gradient descent with momentum, and we also have two types of momentum, the momentum and the Nesterov momentum, where we apply the velocity first to the model parameters and then we calculate gradient estimate. And we also talk about the various adaptive learning rate algorithms, which we can combine with stochastic gradient estimate and either the Nesterov momentum or the naive momentum based algorithm. And the presently most researchers use either the RMSProp or the Adam optimizer because they work for both convex function and non-convex functions. And luckily, in most of your cases, you will find that these algorithms are already implemented. But the takeaway point may be that there is not a unique solution of a problem that this will be the best. And if you find that you are not getting the best result in terms of your learning or the validation error, so this presentation should give you some tool that by which you can select that where you should change that. Like one image classification problem, I told that they put a stopping condition on Adam optimizer and then switch to stochastic gradient descent. So similarly, you can also mix and match these algorithms like Adam optimizer with Nesterov momentum and vice versa, and check out these combinations that which one is working best for your particular application. So with that, I will end this presentation. So